Yeah, so good morning. Welcome to UMBC, the home of Harp 2 on PACE. So my name is Brent McBride, and I lived Harp 2 and all of its predecessors that you see on the table for the past 10 years. What you see on PACE today is really this long of a development. It has been about 10 years to get polarimetry on PACE, both Harp 2 and SPEX 1. But from the UMBC side, it has been a pretty interesting journey, and you'll see a bunch of this today. My question that I think PACE will solve is, when will a cloud start raining? Right now, we're in the era of certainty. We're not asking if, we're not asking what, we're asking now when about science. And a lot of the things that you see, even in this image on the first slide, can give you a hint of where we're going. This is an image of a cloud field that you might have some intuition about. But this one is, for many people, entirely new and completely alien. And we'll talk more in this lecture about why that is and where that comes from. One of the most important questions in our field, and one of the simplest ones and also one of the most frustrating ones, is this: what is a cloud? I know I just said we don't ask what really anymore, but this one's a big deal. And I thought for this we should ask the LLMs to see what they think. Because why not? We should embrace it. This is part of our culture now. So this is one of the language models. I asked it just, what is a cloud, with no context, to see how it would do. And what I got was actually decent and in context with what I'm interested in. So this LLM says a cloud is a visible mass of tiny water droplets and ice crystals suspended in the atmosphere, which is a pretty bold statement already. We've got some two terms here that I'll talk about in a moment: visible mass and tiny. And then you get this massive spoiler about every cloud in the sky. If you're not familiar with clouds, this is a massive deal in remote sensing. That, again, there's that when that I was talking about earlier. Clouds form when moist air interacts with microscopic aerosols. Right? So every cloud that you see in the atmosphere comes from condensation nucleus, these seeds, dust, smoke, salt, that water vapor then condenses onto. So the LLM actually does a pretty good job with no context about what a cloud is. But it also does what the LLM does best in asking you if you're actually interested in the atmospheric version of the cloud or the computational version of the cloud. So B+. So the visible mass. Right, this is probably my biggest stickler with the LLM, the visible mass, because I think what it's talking about with the cloud is that it's taking the human experience of what we experience clouds to be. We can see them in the sky, but really from satellite, we have the ability to see clouds in ways that we can't see with our eyes. This is an image from PACE OCI off the coast of Chile in South America. And this RGB is made in a very special way to emphasize the wavelengths of the human eyesight. So if you were strapped to the bottom of PACE, this is what you might see over this area. But if you had eyes in shortwave infrared, so wavelengths much longer than what we can see, and you were able to look at the same scene, you might be able to see something vastly different. You can see all around the TVs, there's this massive green swoosh across the data. And this is showing you the difference between ice and water clouds. So the green is all cirrus, it's all ice crystals. And we know that because of the sensitivity of ice to this 1378 nanometer band. It's not necessarily ice that this band is sensitive to, it's more like large particles. But the largest particles high up in the atmosphere tend to be ice crystals. And so this just shows you that clouds are not necessarily a visible mass. It can be a shortwave infrared mass, or even a thermal mass. We get information from clouds in wavelengths that our eyes can't see. The LLM also mentioned this word tiny, which is actually a gross over-exaggeration. Tiny is really not enough to really describe how small these things really are. Here's an example of the aerosol particles, just not to scale, but to give you an idea of the ranges that we deal with. Fine mode aerosol can be this tiny. It's just a little point on the screen. You might not even be able to see it. And then these massive aerosols like sea salt can be 100 microns. The cloud droplet, like the LLM said a bit earlier, is a result of water vapor condensing onto these aerosol particles and forming a small mass. There you go. 10 microns is a typical size for these cloud droplets. As the cloud droplets grow, they become drizzle mode, so they could reach sizes of 50 micron. But what we're really interested in here is what they do on the way to precipitation. This is the question that PACE may be able to answer. That's how big a rain droplet is on the same scale. It's just way off the screen. I have to hold it down here like this. But to actual scale, that's how big a rain droplet is. This is true to size, 2 millimeters. And just so you see the scale, this is your human hair width. On the same scale, this is the size that we're talking about. So when I say tiny is a gross over-exaggeration, it really is. We're talking about stuff you can't even see. So that's the question. How do we get from cloud drop to rain? So we went from the really tiny and made the argument that this stuff is really, really, really small. But we also, from space, try to attempt to measure this. These really small things, now we're measuring them at 1 kilometer or 5 kilometers, 10 kilometers. That almost seems impossible. But we still do it. This is an image from Aquamotus just a few days ago. Aquamotus has been up in space for almost 30 years now. And we can get at the pixel level an estimation of this droplet size, cloud effective radius. So how do we do this? This doesn't make any sense, right? We're talking about stuff on the order of microns, and now we're getting an estimation on the order of kilometers. That seems a bit wild. But this is the reality. We can't measure a droplet in 1 kilometer. If you're thinking you can measure an individual droplet, it's not possible. What we're doing really is we're measuring a wider range of droplets. So it's a bulk distribution. Really what the light is doing after it interacts with many, many, many subpixel droplets. And we can define what this looks like. We can call it a droplet size distribution. This is one typical form. And we can characterize it as a function of different shape parameters depending on the cloud itself. So these shape parameters I'll talk more about in a minute, but they define the range of sizes and the amount of droplets that are inside the cloud parcel. For climate, there's very specific cloud parameters that we look for, and we've been studying with PACE and with MODIS and with VIIRS, other instruments in space, for 30 years. One of them is optical thickness. Optical thickness is an interesting one because it's not really that intuitive. We think of thickness, we think of this distance, this physical piece of something with heft. But the word optical is key. So I always like to think about this as if you're riding on the back of a photon. Of course, it's impossible. But if you're riding on the back of a photon, lassoing into a cloud, what does that cloud look like to you? The photon has all sorts of energy, and as it starts banging around inside the cloud, it's going to distribute that energy, and it's going to lose some of that energy in more and more scattering events. If you scatter a lot, then you have high optical thickness. And if you pass through relatively easily or scatter just a few times, that's low optical thickness. This is very important for climate science. Now, the other two that I mentioned earlier, effective radius and effective variance, they're shape parameters, but they also give us some intuition about the droplets themselves at the top of the cloud. So the effective radius is, again, more of like an optical property. It's a physical radius in a sense, but it also is some measure of how likely it is that the light will scatter after it encounters that particle. The effective variance is the big one. This is the one that HARP2 can bring a lot to the table with. It's a measure of how heterogeneous the droplet sizes are in the pixel. This is something that so far we have not been able to measure from space. And there's many other parameters here. So I'm only going to focus on these today, but there's many other ones that are part of the PACE products. I fibbed a little bit. So I said that we can measure the droplet size distribution, but we're not actually measuring it directly. We're measuring how those droplets interact with sunlight. And that's really at the top of the atmosphere what we measure. We measure the sunlight coming up from the clouds. For the past 30 years, we have measured this information from 2 different wavelengths. One of them that scatters light intensely in the visible, and one that absorbs some of that light in terms of the droplets themselves. So what I'm talking about is a wavelength like 750 nanometers in the visible and something like 2.6 micron in the shortwave infrared. And this energy that we're interested in is called radiance. It's watts, which is energy per time, passing through a certain area in a given wavelength and in a given direction. That's the steradian bit at the end. This information is directly correlated to cloud properties like effective radius, the size of the droplets, and the optical thickness, how thick that cloud appears to you if you're a photon. We can correlate this information to incident sunlight and get a relative factor called reflectance, which takes this radiance and corrects for any viewing geometry or the amount of sunlight that's coming into the atmosphere at the top of the atmosphere. And so you can do a lot of like band-to-band studies with reflectance that you can't necessarily do with radiance. But these are very, very important. And I want to show you where this comes, right? This information, this intuition about the cloud optical thickness and the effective radius allowed us to build this climate record of cloud properties over 30 years. This is data from 2000. This is one of the first data sets from this MODIS Terra instrument that measures radiance at the top of the atmosphere. And all the different colors you see are either the particle size of the cloud field in water phase or in ice phase. Water is this warmer colors, ice is the cooler colors. Global coverage. And then look, 25 years later, we're still using the same algorithm today. So this is our climate record in action. But there's a lot of assumptions we made in these early studies of clouds that we cannot avoid anymore. So in order to get the maps that you saw earlier, we had to first assume that every pixel was independent. Like the light from neighboring pixels was not interacting with the pixel that we're interested in. We also assumed that the clouds were slabs. They were just flat. They're plane parallel. And the interaction with light was one-dimensional. So these are the hard truths that come out of this retrieval. Clouds are not one-dimensional. They're not even two-dimensional. They're 3D. The big deal is that at high latitudes, some clouds can be illuminated from the side. And so when we only measure the light that's coming up from the clouds, they can actually make it seem like the cloud droplets are smaller or larger based on how bright that side of the cloud is. And we know that's fake. Verticality matters too. The signal at the cloud top isn't just coming from the cloud top. Right? It's coming from some locations inside or even down by the cloud base. And it depends on what wavelength you use. And also, this one's a big one, subpixel heterogeneity. So in the atmosphere, pixels are not necessarily all cloudy or all cloud-free. There could be a mixture of partly cloudy pixels, and then how do you deal with that? So far, we've been trying to retrieve the duck from its shadow, when in reality, the duck is three-dimensional. Right? So this is the allegory of what we've been doing. It's a whale. And this is the big one that PACE can make a massive improvement upon our climate record. The effective variance, the width of that size distribution, cannot be retrieved from radiometry. So this puts MODIS, VIIRS, and OCI at a slight limitation. If you try to use a cloud droplet size distribution to retrieve information about your droplet size, you need to assume this value of effective variance, the width of that distribution. And if you assume different values of this effective variance, it can lead to some biases in your effective radius retrieval. Why do we care about this? We care about this because effective radius correlates with the light. And we can make that one-to-one connection between how big the droplets are and how much light they're sending back to space. So it has big climate implications to get the effective radius correct. So this is where we are with PACE. There's your cloud scientist on the left. There's your clouds on the right. And with PACE, polarimetry is the big elephant in the room. For those of you that aren't familiar with polarimetry is the study of the electric field of a photon. So unlike radiance or reflectance, that's looking at all the light coming up from the Earth system, polarimetry is more interested in the amount of that light that has a very specific electric field orientation. The electric field here is given in the red. So it's these oscillating amplitudes that move along the flight direction of the photon. From the detector surface, we're looking at photons coming right into the focal plane array. So we're not looking at the light from the side, we're looking at it head on. And so to us, this oscillation looks like an up and down. And so depending on where that oscillation is relative to a certain axis, that can give us the polarization information we're after. The radiance is encoded in this angle. And we can use specific filters. I brought a few of these over there you can play with a little bit later that can take light of any arbitrary polarization state and select just one of them. This is the mechanism that HARP2 is based on. In real life, we can use this to cut glare from swimming pools. So swimming pools will, as the light comes in, It's full of all sorts of different types of angles of polarization. And then when it reflects off the surface, only one of those angles of polarization is going to pass. It acts sort of like a polarizer. And so if we have our own sunglasses there at a specific angle, we can completely reject that angle of polarized light and see straight through the surface. This is the kind of information or the intuition that HARP2 is based on. Here, we don't want this information. We don't want the polarized light. But HARP2 uses that for science. And this is the big deal. This is why polarization matters for clouds. The very left is what clouds look like from aircraft. If you were to put OCI or HARP, or OCI or MODIS or VIIRS on an aircraft, these radiance-only instruments. But if you were to put HARP on an aircraft, you would see a bit more information in the cloud that's connected to the angle of that polarized light, the angle of the light that has some large-scale angle to its electric field. That's this one here. You can see there's many, many, many more rings inside that structure there. And one of the things HARP2 can do is measure those rings. Why do we care about these rings? This is just a beautiful thing. Why does it matter? We care because these rings are connected to the droplet size distribution itself. The character of these rings, the distance of the spacing of the different rings, the intensity of them. It gives us a one-to-one link between the polarization information and the droplet size distribution. Because each one of these rings, each one of these cloud bows is unique, that means each droplet size distribution is unique. And that means that we're sensitive to effective variance. We can retrieve the entire size distribution. But HARP's not the only one to have done this. The past 20, 30 years, we've seen many, many, many different experiments, many different instruments that have demonstrated this technology. In RGB, man, these cloud bows explode in colors. You see from Pulled Air in 1994 and the aircraft instrument OSIRIS. RSP has been the community standard for a long time. The way that RSP measures, it's got this single pixel that scans through tons of angles and gives you a really tight angular resolution on those ring structures. You've got MISPI from NASA JPL, has a different way of measuring the cloud bow. And then recently there was an instrument from the University of Munich in Germany that measures the cloud bow with 2 different cameras off nadir. But the science is all the same. So the reason why all these instruments exist is because we want to get more information about that droplet size distribution. And that brings us to HARP2. So this is data from HARP2 on pace. 2 days worth of data, we get global coverage. But this is maybe not that interesting. We get this from MODIS, we get this from VIIRS, we get this from OCI. What about this one? So this is what the Earth looks like in polarized light. Again, this is the light that just has a preferential orientation to its electric field. And man, does it look alien. There's a lot of stuff going on here, but what I'm interested in is this structure here at the top. These are the cloud bows. And the other thing I want you to take away from this is that this is just one angle of HARP2. HARP2, you can see over there, has this wide field of view front lens. And that front lens means that we can, as we fly, we can measure the same target on the ground from many, many different angles as the target passes through the detector space. So we can make 90 of these different maps if we only care about small parts of the detector at once. So this is what the Earth looks like in polarization from a very far forward view. This is what it looks like at nadir, so looking straight down. You can see the cloud bow shows up again, different geometry. And this is what it looks like if you look backwards. So it's only 3, but there's 87 more of these maps I could show you. And 87 more of the maps you can play with if you download the HARP2 data. But the important part here is that you see that the cloud bow changes. And that's a manifestation of viewing the clouds from different angles. You get different information when you add all of this angular bits together. And that's really what HARP2 is doing. It's flying over the cloud. There's the target pixel, and it's seeing it from many different angles, building up how that cloud scatters light, 4 different wavelengths. And at 670 nanometers in the visible, it can do this at 60 unique viewing angles. All right, so let's look at how this actually works with a bit more intuitive. Let's use a HARP beer. Right, so HARP beer, as we're flying over it, you can see in the video. Let me see if I can go back. Yeah, so you can see in the video, you're seeing parts of the bottom of the beer, and then you're seeing the top, and then as you're flying over, you're seeing some of the back. This is all information that HARP2 is grabbing about the atmosphere. Of course, HARP's not measuring HARP beer, but this gives you the intuition. And this is what we get with MODIS spheres and OCI. So you get one view, one angle. We've done incredible amounts of science with the one angle. Don't let me make that seem limiting. But we're adding so much extra information when we look at the same target from multiple angles. So if you pull the HARP 2 level 1C, it can be a bit confusing because the cloud bows don't look like this. This is what the cloud bow looks like if you just take an image with HARP 2 like it's a regular camera. Project the image on the surface of the Earth, the cloud bow looks like rings that I showed you earlier. But in the level 1C, we're doing some processing to extract angular information from this level 1A. So these yellow lines you see are representative of single angle views on the ground. So 45 degrees forward, 45 degrees backward, nadir, things like that. In level 1C, the cloud bow is going to look like this. It's going to go from this curved space to a linear space because we're taking sequential images and just building up what the ground scene looks like, but just from one of those angles. So you can look at each one of these like the beer. This top one is one view of the beer. This one's the other view of the beer. This one's the back view of the beer. So it's really just how the cloud looks at different angles. But the beauty of this level 1C is that all of these angles are geolocated to the same latitude-longitude grid. And so what does that mean? You can take the same pixel in this angle, in this angle, in this angle, in this angle, and that represents the same cloud, just viewed from different angles. How does that manifest in the cloud bow? Well, if you plot that, again, same pixel, just different angles, that's the pixel that goes to this data point. That's the one that goes here. That's the one that goes here. That's the one that goes there, and so on. And so that's how we use HARP 2 data to build up the multi-angle information about the cloud field and anything else. This works for aerosols, land, and ocean. But really, it's more than just the multi-angle. Really, what the cloud bow is encoding is the droplet size distribution. I mentioned earlier that the cloud bow can be a variety of different orientations, and the rings can be different sizes, and the rings can be different distances. The distances of the rings encode information about that droplet size. That's the top plot here. The amplitude of those rings encodes information about the effective variance. And they are nearly orthogonal bits of information. And so we can simulate this using mean theory. We can compare it directly to the measurement that we see from HARP 2, and we get out what we're interested in. We get out the effective radius and the effective variance. It's a very simple algorithm, but it's a very powerful one. There's two ways with HARP 2 that we currently are doing this kind of analysis. One of them is called the polarimetric fit. And it's exactly what I just said. So we're comparing the measurement from HARP directly to what I'm calling P12 there. It's the theoretical curves that are modeled by mean theory, our expectation of how liquid water droplets polarize light. This is some examples of what HARP 2 data looks like here. So as a function of scattering angle, or the angle between the satellite and the sun, you do have this massive rainbow and then other smaller rings. It's like a cross-cut of that video that I showed earlier. This one over here is much more powerful. So the rainbow Fourier transform was developed in 2012, and it uses a very clever mathematical framework to treat all of these guys, all of these simulations, like a Fourier series. It treats them all like sines and cosines in a sense, and builds up potentially cloud droplets that have more than one size distribution. So cloud pixels may have more than one kind of droplet grouping inside of them. And the rainbow Fourier transform can potentially tease that out. One of the details with the parametric is that you always have to assume a single mode. So we're always going to be a bit limited there. But there's a lot of really interesting science to come with the RFT. And I want to talk a bit about how we did this retrieval. So the first time we ever did this with HARP, 2020, familiar name, we did it from aircraft. And so this is what we did, again, flying over the same cloud pixel, building up the multi-angle. But because we have a wide field of view, there's many pixels that we can do this retrieval over. And we can start looking at interesting teleconnections between radiance and effective radius, radiance and effective variance. And you start to see some interesting things showing up. Right at the top of the clouds, which is here, effective radius tends to be larger. On the cloud edge, tends to be smaller. Effective variance seems to be opposite, right? It seems to be a bit more narrow towards the top and a bit more broad towards the side. So these are some really interesting science tidbits that we're getting from polarized light that we never had before. This is all we had from space before. So this is just one granule from aircraft, one example. But now we have, every 3 days, that same intuition from space. This is your true color. This is your effective radius. And this, for the first time, at 5.2 kilometer resolution from space, this is your effective variance. This is a massive advance for PACE. This has never been shown at this resolution. And then just a blow up of the effective radius that we're seeing. We get a lot of information in the Southern Ocean where a lot of clouds are. We also get there's some regular marine stratocumulus, these really large spanning cloud systems that hang out on the side of South America, south of California, and also Australia that are really good examples of this. And also, again, a big blow up of the effective variance. So you might notice I didn't really address this question yet. I spent a lot of time talking about the history, a lot of time talking about HARP, a lot of time talking about polarization. But yeah, when will the clouds start raining? But really what we're asking is, how well can we identify a specific cloud process from space? It's called collision coalescence. But you might be thinking to yourselves, I don't really care about precipitation. Why does this matter to me? Well, the obvious, right? So it's what brings us our food, and it also drives our weather, right? It's part of the water cycle. But recently, there's been a lot of cases in the news where precipitation has played a direct role in world events. We're seeing an increase of wildfire incidents. We're having to do more cloud seeding in the southwest of the country because of droughts and wildfires as well. We're trying to get more water onto those areas. And this has led to a lot of property loss. This is a lack thereof precipitation. Also in Maryland, if you live here, we used to have a stormwater runoff tax for a bit. So if your impervious surface on your property was of a certain size, you had to pay a bit more state taxes. So there's money involved in precipitation. There's of course acid rain when there's acidic particles getting into the water cycle and starting to damage buildings and other things. And you also have current events like the flooding in Texas from a very extreme precipitation event that happened. And there's also an interplay with greenhouse gases. So as the world warms, we do expect more extreme precipitation events. But really, what's the science here? So as droplets start forming in a cloud, it's this interaction between water vapor and aerosol particles I mentioned in the beginning. And a lot of that growth is condensation driven. So it's this water vapor just coming onto the aerosol particle, latent heat is released, and then this feedback loop continues that brings more and more water into the droplet. The updrafts send this guy up to the top of the cloud, where they see their largest sizes, largest cloud sizes, might I say. And that's where we expect to see the drizzle mode that I talked about earlier. This is some intuition from remote sensing. So this is from the SpecMax instrument doing some active cloud measurements. You can see that the effective radius does indeed grow as a function of altitude. This is some information coming from large eddy simulations, which is modeling of cloud fields using Navier-Stokes equations. You can see in this case, with models from a different instrument, that we also do see physics-based modeling showing the same thing. Right? The effective radius grows towards the cloud top, and we see that the width of the size distribution also gets wider. So this is science. This is science that's going to tell us a bit about this cloud process and how we're going on the onset of precipitation. The last thing that we need to think about is where does the cloud information come from? So we looked at remote sensing, we looked at LES. We also have evidence from in situ instruments which fly into the clouds and measure the droplets. They also see the same thing. Cloud droplets increase with height. So this is pretty well known. But the interesting bit is that if you, again, compare radiometry and polarimetry, you see into different parts of the cloud. And this is part of the reason why it's been so tricky to study precipitation from space. Different wavelengths here, 1.6, 2.1, 2.2, 3.7, they have different penetration depths. And so the effective radius, the droplet size measurement at the cloud top actually comes from an integral of the different sizes inside the cloud, different amounts. Polarization is really only looking at the top. So maybe we have an opportunity to decouple information from the top from everything else that's going on. But what else is happening at the top? So continued growth of the droplets are going to force them to collide with themselves. This is the magic number, 20 micron, that is the relative limit where the physics starts to play a role. These droplets start to tend to fall. And as they fall, they start interacting with other droplets. They're colliding, and they also might be coalescing with these other droplets as well. So at the cloud top, what that means is that we expect that the droplet size distribution should split. We should see two different distributions. We should see one representing the cloud droplets, and we should see a larger one that's representing more of these bigger guys that are starting to fall through the top of the cloud. And this is going to give us the onset of precipitation indication that we're after. Let's go back to talk about that rainbow Fourier transform, that really interesting cloud retrieval technique that relies on the mathematics of those curves. So before we've talked about the cloud bow, these rings, but really we only talked about them from the perspective of one droplet size distribution, one size. But here, the Fourier transform doesn't assume a droplet size distribution. It doesn't assume that the clouds are doing necessarily anything except for being of a certain size range. And so it can measure any kind of cloud bow, even these naughty ones that don't behave like we expect with a single droplet size distribution. So what you're seeing on the top here is a mixture. So there's two different distributions in the pixel, and they're creating in the black these bizarre looking oscillatory patterns. But we can use the idea of the Fourier transform to deconvolve this signal into its component parts. We can say that this black cloud bow here, it actually is two distributions coming together to make that polarized signature. And why is that really powerful? Because we can track how the droplet size distribution is changing from cloud edge to cloud center, and identify exactly where the precipitation cores could be happening. This is a study by Ken Sinclair in 2021, where he used some of that research scanning polarimeter data during the NASA Oracles campaign, looking at how the cloud bow information changes as you go from cloud side to cloud center. You might have to zigzag your eyes down here, but you're seeing the cloud side, and then as the instrument is flying over the cloud, you're starting to see the evolution of the second mode. This cloud mode here that's appearing closer to 20 microns is just growing and growing and growing and growing until eventually, at the cloud center, it is the dominant mode. And this is the information that HARP2 is going to be able to provide to us for the first time in space. It's a product of the resolution, it's a product of the multi-angle sampling, and it's a product of this new RFT algorithm that so far in space has not been able to be applied to any kind of instrument like HARP. So what I want to do is I want to end on this. If you've never thought about using HARP2 or SPEX1, it is truly a treasure trove of new cloud science. There's all sorts of questions that we have about clouds when we compare the information coming from HARP or coming from MODIS or OCI. Those two information should agree in most cases, but sometimes they shouldn't agree. And in which cases, why don't they agree? And then why do they agree in some cases? A lot of these questions are still somewhat open. We could potentially use polarization to better understand where our information in the cloud is coming from. As I mentioned a few slides ago, the polarization is really just cloud top. And the information in the cloud, using radiometric information, it's more or less coming from different places inside the cloud. And then I mentioned earlier that there are these 3D effects. So if a cloud is illuminated on one side, it can make it seem like the droplets of the cloud are a bit different than they would be if the cloud was illuminated from the top. And we know that's just an artifact. Something that's really interesting about polarization is that it's a bit insensitive to this effect. And so there's tons of interesting science to look into here. But what else? Maybe these properties have some really interesting correlations with aerosol microphysics or even phytoplankton. These are all things that PACE is uniquely capable of allowing us to do. One of the interests of mine is if we can use the cloud retrieval itself to improve the calibration of the instrument. And then if you really want to get a bit unorthodox, take a look at SPEX1. SPEX1 was really developed to be an aerosol instrument. It's got 5 angles, 109 different wavelengths, narrow swath, really, really, really good at aerosol science. But it's imaging the same kinds of clouds that HARP2 is. And it's sensitive to polarization, it's sensitive to hyperspectral. So what's there? So I encourage you to take a look here, I encourage you to take a look and ask questions about the cloud information that you're seeing, even if you're not interested in clouds. And so with that, I'll end, and I want to leave some time for questions too, so thanks for your attention.
Thank you very much, Brent. I will pass the microphone for questions.
Hi, Brian. My name is Piyush. I'm from Esron. Very interesting and very innovative algorithm. My question is about what are the challenges you will find when you distinguish a liquid cloud and ice clouds with the polarimetry? And is it possible that you can also look for the cloud types, not the liquid and ice, but yeah, within the liquid cloud? And I'm sure that there is an issue with the mixed clouds also. But yeah, you can just give some highlights on that.
Yeah, sounds great. So thanks, Piyush. And we're pretty lucky here as well, because we have a lot of cloud experts in the room. Also Dan and Kirk and Sean as well. If these guys have any intuition, I may just also send it to them, because they work with more of this data more directly than I do. But some of the really interesting bits about the polarimetry that HARP2 and SPEX1 can do together even is that the cloud bow that you see here is unique to liquid water. So if you see it, you know you have liquid water clouds there. Ice does not have the same multi-angle structure. So ice is made of all sorts of different kinds of particles, rods, cones, dendrites, these other shapes that tend to destroy any large-scale polarization at different angles. And so being able to measure the multi-angle gives you an almost immediate identification of cloud phase. Now with mixed phase, I'm not as confident in that one. Maybe Dan or Sean or others have a better idea.
It's actually part of our current PACE science team project, is to try to integrate 2 very different methods of identifying phase from total radiance and from polarized reflectance. We also don't have the ICE algorithm in production yet. So there is an ICE algorithm. It tries to retrieve habit. Or actually, its main retrieval product is this asymmetry parameter, which mainly just describes how much light gets scattered forward. For MODIS, that's an assumed property. We basically assume very rough ice globally everywhere, because very rough works out. But it's not necessarily true if you're seeing directly at the cloud top. And because polarimetry can only see very, very much at the cloud top, it can actually start to say, at the cloud top, this is what it actually is. So we're really excited about it, but yeah, there's a lot of work still.
I'm really excited to see what we can do with SPEX1. I know that part of the team is developing a neural network type application for the droplet size distribution, so I'm really excited to see where that goes.
I have a question. I just kind of want to check my understanding, since this is all fairly new to me, but it was very well presented. So when we're talking about the, when you were getting onto sort of when we have our bimodal distributions of the effective droplet size, visually, so you were showing us pictures of cloud bows that have nice concentric rings. Mm-hmm. I'm guessing when you see the nice concentric rings, that's probably not a bimodal distribution. It kind of shows up as that's probably something that has more of a consistent droplet size, and maybe when it's a little less visible as concentric rings, it's not so much that could be a situation where we're developing into, basically that bimodal distribution, possibly. Like it won't be as visible to the eye as concentric rings, is that right?
Yeah, the visible to the eye is a tricky one. So I showed a slide earlier. Let's see. Yeah, so these are more or less crosscuts of that ring-like structure. So let's see, if I just go back a bit. I don't know how far this is. So if you take an intuitive image of the cloud bow, it looks like that. You have a really strong ring at around 140 degrees scattering angle, and then you have these supernumerary bows coming in. So that's the visual that you get. And if you have a monomodal distribution, just one mode, you should get something really nice like this, like rings that pretty much match what you see over there. But if you have 2 modes or more, you may still see rings, even visually. And this is an example of that. So you have, if you look at those crosscuts again, so again, this is the really big ring, the really bright one. And then these are the supernumerary ones, the ones inside. You still have some oscillations here. So if this cloud on a broad scale has a bimodal distribution, there is a chance you will still see supernumerary bows. But the other detail here is that the effective variance is really important for this as well. And that's one of the main differences between the 2 algorithms, is that it's not like, let me see if I can get back to this. Yeah, so this one, the parametric fit, again, just simulates or it expects one mode of the distribution. But that doesn't mean it's going to try to avoid pixels that have multi-modes. It's going to try to still retrieve on them. It has no idea what it's looking at, but it's going to still do science. And the consequence of that is that if it does have a bimodal distribution in the cloud field, this parametric fit is going to swing wide on effective variance. It's going to think it's a really wide distribution because it's going to try to satisfy the entire curve. The curve is multimodal. It's going to have a much broader distribution, at its base. And so it's going to, you're not going to see very many rings in that case. It's just going to swing wide on effective variance, and it's not necessarily going to be too useful. It'll identify that there's heterogeneity, but it won't tell you what kind or where specifically it is. Yeah, very nuanced question. Yeah, Kirk's back there.
Just to add a little and explain more about the rainbow Fourier transform, can you go to the slide where you showed?
It's probably down here. It's one of these.
This one, yes.
Yeah.
So it's called the rainbow Fourier transform. There isn't a Fourier transform, but if you know what a Fourier transform is, that's taking a shape and you fit a sinusoid to it, right? And so you're trying to identify particular sinusoids. The rainbow Fourier transform, instead of using sinusoids as the basis function, it's using sort of like a monomodal size distribution of cloud droplets as its basis functions. So you have a whole bunch of those, and you're trying to fit them. So you can kind of think of these 2 middle cases, the C and E, that's sort of like 2 different waves constructively or destructively interacting with each other. And so you can still see the shapes there, but really what the rainbow Fourier transform is doing is decomposing that back into the original size distributions. I don't know if that helps I guess if you know what Fourier transforms are and that kind of thing.
Yeah, and there's many, if you look at this presentation, this paper down here is exactly the description of that algorithm. So I encourage you to take a look if you're interested.
Hi.
Yeah, thanks, Kirk.
I don't know much about clouds, but I know clouds are distributed across different heights, high level, middle level, and lower level. So can you estimate the cloud height? Because depending on the height also, because low level and middle level clouds are mainly contributed to precipitation. So can you identify that?
Yeah, and that's something I really didn't touch on here, but if we go back to, let's see, where's my Harp beer? Okay. Here we go. So this one has nothing to do with polarization. This is just a manifestation of the fact that Harp 2 can see the same target on the ground from many different angles. So traditionally, we get information here, but if you look at this one, and you look at this one, these furthest 2 angles, encoded in this is actually information about the height of the beer, because the top of the beer is located in different portions of these images. And so if you treat that as a cloud, you know where the cloud is in latitude, longitude space, and you can use the apparent displacement between the top of the beer here in both of those angles to calculate the cloud height directly. It's more like stereographic imaging. If you've ever gone to a museum and put your face into this binoculars with these 2 images that almost look identical, and they want you to cross your eyes. So if you do that, you'll get this almost pseudo height coming out of those 2 2D images. And it's a very similar idea as using here. You essentially just use the geometry of the observation to calculate cloud height. And it's independent to the way that it's traditionally been done with MODIS or VIRS type instruments, which is used the amount of carbon dioxide in between the cloud and the top of the atmosphere. Yeah.
Thank you.
But, yep.
Related, how do you deal with that parallax effect when you're doing geolocation? Like, how do you know you're looking at the same cloud?
Oh no, Hannah just went.
Yeah.
That's a really tough problem. Yeah. So it's something I'm gonna kick to Dan.
Okay. The answer is we don't. Because so for low-level clouds where we're doing the liquid retrieval, this parallax effect should be small, especially if you're at 5 kilometer resolution. So we do have hope to do a cloud vertical profile like identification of height, but it's really going to be very capable for cirrus and higher level clouds where you have this big contrast between the location on the surface we're registering to and how high vertically we are in the atmosphere where the cloud is located. But yeah, you need contrast, and here because you're close to the beer, relatively speaking, and not all the way up in space, you can see this parallax effect very strongly. But if you were up in space and you were looking down at that beer, it would zoom past you, right? So, if you registered it all to a common location, there wouldn't be as many distinctive differences. But yeah, there's new information in this data, and we're going to learn something from it. But for now, the polarimetric liquid retrieval hopes that it's not a big deal. But it isn't a big deal. We checked also.
So you can't, but it's not a big deal. It's very encouraging.
Let's do one more. And
Yeah, thanks, Dan.
while I'm walking, I have to ask, since this picture's on the screen, did you purposely include glint in this experiment?
Oh man, I'm a true atmospheric scientist. A lot of glint, actually, different.
I just want to add on to that.
Yeah.
We don't have it yet, the cloud type accounting for that. In fact, the file format that we made, level 1C, when that file is generated, it takes as input a terrain height, which can easily be swapped out for a cloud top height. Now, we talked about polarimetry here for clouds, but I just want to remind everyone that OCI is also a very capable cloud remote sensing instrument. One of the things it does do with a spectral technique is a cloud top height retrieval, and we're still validating that. So that's one of the ways that we could recompose. So one of the big questions is how do you regenerate the files to deal with variable heights? And then finally, Sean over there is also working on other ways of coming up with a 3D tomography of the clouds using just the multi-angle. So imagine taking this thing here and deriving the shape of the beer bottle based on all those different images. So the short answer is we don't have it yet, and there's multiple pathways to get there, and we're just not sure which is the best yet.
So this slide really made me think, could we use multiple angles from a polarimeter to create a digital elevation model of land if it's cloud-free? Has anyone ever done that before? Because that would be helpful for watershed mapping, flood.
A bunch of different things.
Yeah.
Oh yeah.
But I mean,
Right.
Oh yeah.
What? With, yeah.
Mm-hmm.
Right, like triangulation of all these different key points, like what we do with drones, Alejandro.
Yeah.
There's other sensors that have higher speed
Right.
resolution.
Right. Cool.
Can you ask it over a donut, Eli?
Well, I want to take a shameless plug for Polar Geospatial Center's Arctic Den, REMA, and products, which are exactly that. And computer resolution.
I'm sorry, what were the units? Meters? Thank you.
Amazing.
Okay,
That's okay. So one last thing before we transition, I brought a bunch of toys for you today. One of them is not a toy, but some of them are mostly toys. So this, if you've never seen HARP 2 before, if you never come to UMBC and come to our labs, this is what HARP 2 looks like on a 1-to-1 scale on PACE. The size is important to see in person. I think you see all of this multi-angle and polarimetric wide field of view stuff, but it's coming from this little guy. And HARP 2 is called HARP 2 because it is the second version of a standalone CubeSat instrument that we had in space for a bit. This guy was launched in 2020 and flew in the orbit of the International Space Station. And it was just a technology demonstration. So we have data from it, but it's not necessarily public. If you're interested, you can ask us for it. This guy is the one that's not a toy. This is AirHARP 2. This is the instrument that flew on board the high-altitude ER2 last fall during the PACE-PAX campaign, so the actual instrument itself. The closest anyone can get to HARP 2. But the instrument is a 1-to-1 copy of HARP 2 on PACE. So when you get a chance throughout the day, take a break, come up here and take a look at all the hardware that we have. There's also some more internal components of HARP that are also here. So the polarizing filters that are involved in the measurement itself of the IQ and U Stokes parameters in the level 1C. We also have the Phillips prism that does the polarization separation of the light to each one of 3 of HARP 2's detectors. And then we have a detector. So this is the actual focal plane array, well, a copy of the focal plane array that's inside the instruments. And then finally, the cage. Again, the scale of stuff is still shocking to me. I've been here 10 years. I'm still amazed that we can get this kind of science quality at just this size. So again, thank you so much for your attention. And I'll be around for the morning, so if you guys have any questions or anything. Yeah. Well, thanks.